All right. Donnie, did you want to start with a short overview? Or we can do them later.
I could.
Make a couple of sentences, just say what's.
Well, I think, so I figured that we could start this off with just like seeing how far quantum computing has come. And I won't bore you guys with like a detailed list of the history because it dates all the way back to the 60s and such. But it really started like the 1970s once like the first quantum Turing machine was made, which tried to, I guess, prove that it was possible to use quantum information to analyze these quantum systems. And later it was, you can start with the qubit. No, it'll come naturally during like the.
Okay, if you just ever want to like insert the
Right.
any cool facts. Okay. So I'll start with just like gentle introduction into gentle but deeper introduction into the qubits. I know that those of you who attended last semester, you probably already know some concept, but there are also people who are new. But this meeting, there will also be some new facts for everybody because we'll also have quantum key distribution, which is basically the concept of exchanging private keys in cybersecurity, but quantum based. Other Matthew, do you have any? No. Yeah. Yeah. I think. I don't have one, but. Oh, this. Oh, yeah, awesome. Thank you. So, how many of you have taken like basic ENM or physics 2? It's okay if not. Okay, so I'll just briefly introduce the concept of polarization then, because we will work from that. So when we classically talk about polarization in physics 2 class, we have like a filter, which is something like that, and then we shoot some light with wave here, and then we have a wave coming here, and then let's say our polarizer filter has some kind of like axis that basically makes the light a little bit dimmer because we tilt our wave, so-called. And so because of that, if we had our axis like in 90 degrees, accordingly to this wave, we'll have no light coming out because this wave would be perpendicular to this axis of polarization.
I had some polarizers in my bag. That's a problem in case you want to use this.
Yeah, you can
Pass it around.
if you want to just like pass them around. So yeah, polarization is used like in your, for example, sunglasses. And there are also some cool like polarizing tools where you can like see through water because you don't have like light that bends and reflects like from the water surface. So that's like some cool stuff about polarization, but that's how we describe it in the freshman course with wave and blah, 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 blah. And what we know is that basically light is a bunch of photons that are coming into there. But now, once things get quantum, we changed our experiment and completely don't use like this whole wave, and we just use like simple photon. And so what do you think will happen if we just shoot one photon into this polarizing filter? Any ideas? So when we start talking about the simple photons, our classical physics kind of stops working. And what we have right here is a photon that actually also oscillates in certain directions. So it can oscillate here, it can oscillate like that. And so based on that, we can only predict the probabilities of it either coming through the polarizing system filter or not coming through it, or maybe like, so if it's not coming through, that means that the filter has absorbed the photon. And you should see the picture on the next page 2. So page 1 is just like some differences between QC and classical. So when I say QC and CC, it just means quantum computing and classical. Okay. Oh, by the way, there are some pictures demonstrating the polarization effect. So when you see, we're shooting like the light that has that basically contains like unpolarized light. And when I say polarized, it means that it oscillates at a certain direction. And so after that, we have a dim light, which means that the intensity of light is less. But then what happens when we insert another polarization filter that has the axis orthogonal to the second polarizing filter, we see that no light is coming through. And what is interesting about that is that if we insert another filter in the middle, so you see it's like B that is coming here. These two are orthogonal, and then in the middle we inserted the one that is kind of like in between these two, 45 degrees. Then we see that actual light keeps coming through. And that's kind of interesting to us. And so to understand what happens in this situation on a quantum side, we introduce the our so-called polarization vectors. So when we have our polarizing filter, we can say that let this vector be our like polarizing axis. And so from here, we know that this will be 45 degrees and this will also be 45 degrees. And so, as I said, these photons that we're shooting only one, but they can fluctuate in certain directions. And this will be defined as also a vector. And so if we shoot a photon that fluctuates in this direction, then the probability that it will go through this polarizing filter will only be 1/2. So I'll write it as alpha, that it will be 1/2. But we actually can see that the length of this sector will be 1 square root of 2 of this polarizing axis vector. And so what it tells us is that there is a probability of 1/2 of this photon coming through the filter and probability 1/2 of the filter absorbing it. And that's basically how we can also explain the effect that we're seeing here. So for first filter A, let's just break it down this case for simple photons so we get a better understanding of this. We shoot some random amounts of photons, into here, and we have a polarizing vector in this direction. And so we have these photons fluctuating in many directions, and so that's why approximately 1/2 of them will be either absorbed or shot through. And so similarly, because we have now only photons that are polarized in this direction, when we have a filter in this direction, and this is our the vector of photons, we know that the probability of these photons being either absorbed or coming through is also 1/2. And so into force, because now we only have photons that are flying this way, and so into force. And so that's basically is the definition of qubit. The most basic definition of qubit is just like polarized photon. And there are actually quantum computers that are based on photons. There are many types of qubits. There's like ion trap, there's neutral atom superconducting computers, but that's the example that we're gonna work with today. Are there like any questions about that?
So what, I guess, property of the photon is interacting with the filter? And how do you like represent that in terms of like some of the formulas?
The way I explain it is that, so I'm not sure if that's exactly right, but the way I explain it in my head is because photon is also like a wave and it is fluctuating. So if we have a polarizer with, let's say this is gonna be like a hollow space here, and the photon is fluctuating in this direction, so it just like won't come through this direction because it's gonna be like perpendicular for a really small space.
I suppose that would.
I mean, I'm not sure if that's probably just like a really simple explanation in my head. I'm not sure how to explain it exactly.
That's
It's like physics.
yeah, that's an intuitive, I suppose, perspective on it. But I think at least describing some of the quantum theory, because at least in physics, it's mostly about trying to understand what we see experimentally, but we can't really, I suppose, visualize it very easily. The theory itself is the best that we have in terms of understanding, I guess, why the light is halved each time. And yeah, is anyone interested, I guess, in seeing the formalism of how we mathematically represent the process going on here?
Okay. Okay, yeah, I'll write it down then.
Like just what the, I guess, the notation is, and then like how the state evolves from A to B to C.
Yeah, I think that would be interesting. I didn't search that up just because I'm using this as a more like a introduction to what we're gonna use next. But I think that
Oh, yeah,
would also be interesting.
you want me to do it or?
Yeah, you can search it up. Or do you know this?
Yeah.
Actually?
Just the rundown.
So.
Yeah, you can do that.
The polarization as a qubit, fundamentally a qubit is just a two-state system, right? So we say we have these two orthogonal axes. We can call this state 1, we can call this state 0, and you can just think about these things as vectors, as depicted here. So without going into like how these vectors necessarily interact, just think of like if we just have light, say coming into, you go back.
You can.
You go back. The light that is coming out of A, which is in a, you can say, this is a quantum state. Through this goes into the quantum state of 0. So it's a pure 0 state. And you can consider this as like a measurement. And what we consider a measurement is anything that acts physically on a quantum state to, I suppose, change it. It's like interacting with matter or other quantum objects. And we don't exactly know how that works in most instances, so the theory is meant to describe the experiment, and once we have a good understanding, we can represent, I guess, this as an operator, but of course, that's a little bit too advanced. So focusing on just what's happening here as the light's going through. When we have this orthogonal filter, the light isn't allowed, but say we have this other filter in the middle that is a superposition of these two filters. So instead of going to the 0 state, instead, assuming that we're using this filter, sorry for all the arrows, by the way, I'm a little confusing. We remain in a sort of superposition because this isn't necessarily orthogonal to this. So there are components of this vector that are within this vector. And that allows certain photons which have a component within this vector to shift their polarization or the direction of an electric field, because light is an electromagnetic field, but a lot of the effects when it interacts with matter is only relevant to the electric field for purposes that, if you're interested, we can go into a little bit, just like briefly. But yes, sort of the gist of it.
Oh. I thought you're gonna like write like superposition and like not like vectors, but like
Oh,
something with like actual quantum mechanics or something.
right. I mean, this is technically what a superposition is.
Yeah, I mean, that's what I wrote here. I just haven't gotten to that part, but thank you for it. Yeah, you could. You could. I mean, that's exactly what I was about to say next. Yeah, I thought you were asking completely different question.
Okay.
You're good. So, all right. And so is everybody okay with how we describe the polarization with one photon? Okay. Good. So, all right. Then let's move on to actual, just like briefly, I want to mention the operation of measurement. You probably already know that, I mean, I suppose many of you know that the qubits actually exist as we said, as superposition between two. So it's not that there is a probability of this. I mean, it's true that the probability of photon coming through the filter is like, let's say 1/2, but then it's not, how to say it? It's not exactly probabilistic. It's more like the state exists in two positions before we measure it. In superposition between two positions. And so this measurement operation is basically what we can see as a filter. Filter is our single qubit measurement machine, so called. So that's also on page 2. We have bullet points. And as we said, there are 2 orthogonal vectors. This one and this one, which is basically just this. And this is a requirement that we have to satisfy whenever we define our quantum device. And basically, it can be any system that contains these 2 orthogonal vectors. It can be anything like just classical orthogonal vectors, or you can choose like this one and the one that is called Carmelian. We'll get back to it later whenever we'll start about quantum key, start discussing quantum key distribution. And so that's one of the requirements of the our quantum measurements. And so the other thing is that as I said before, the system exists in the superposition between two states with probabilities of finding, let's say one would be a squared and finding 0 would be b squared, as we saw from the geometry that I just erased. And so because of that, we also have such thing as no clone theorem, is because we never know what we're gonna measure, basically. And we only know the probabilities, so-called a and b squared. And so, do you want to elaborate on no clone theorem here, or do you want to discuss it later?
Yeah, I mean, generally what the no cloning theorem is saying that a quantum, I guess, object or qubit can't be exactly replicated like a classical qubit. And it's one of the big differences. So like copying even like memory over from a computer, say like, like pictures from one computer to the other. If it was encoded in quantum information, that would be, I suppose, impossible to do trivially. I'm sure there are ways to, I guess, copy the information over using certain gates, but ultimately it requires more steps. It's not such a trivial problem. But I think we can perform with certain gates, like controlled not gates. And we can get into that. Basically, that's just one of the major differences between quantum computing and classical.
Yeah, so basically we have a certain, what we call a state before measurement. And after we perform a measurement, the state changes. So state is what we define here. And after measurement, it will always be either 0 or 1. And this is just a vector. So what changes is that the state itself changes. It is not that it exists in 1 already, and we have a probability of finding it as like 36%. It actually exists in this form, and then it collapses to either this or this. And I think it should be pretty simple, and many of you already know this. Okay, we have a few minutes. Let's just move on to quantum key distribution, because I think it's the most, at least for me, interesting part of this. You also have it on your handouts. So we have families, and we have, well, and so, as you may know from classical key distribution, they exchange some sort of key, which is just like 0, 1, 0, 1, 0, 0, 0, 1, just like the number of bits that only they know. And using this key, they encrypt information, and only they know the key. And that's why they can exchange their information secretly through some kind of chat. But the problem with classical implementation is that if someone somehow finds this key while they're exchanging them, they can basically decode all their conversations or whatever information they're exchanging. And with quantum key distribution, is, in theory at least, is impossible. And also, quantum technology can also kind of crack this classical algorithm. You can basically enter people's conversation in theory, but not do that. And so.
And further on that was developed in 1994. It's shortest factorization algorithm. Theoretically, well, was actually implemented in the early 2000s, but basically it's able to enumerate the factors for say large numbers at an exponentially faster rate than classical algorithms, which allows it to break things such as RSA encryption. So
with that being said, quantum computers do actually endanger some of the classical encryption methods that existed during that time, still are used very heavily today.
So coming back to actual implementation, let's say Alice wants to encode the message. And so she decides on like some string, let's say, just like some random string of classical bits, and they have a quantum channel. I just call it this, and then they have also a classical channel. So we do have two channels, and speaking of our polarizers, for every bit that she uses a random polarizing filter. And let's say we just talked about the orthogonal basis. So this is and I also mentioned the other one. Which is let's say yeah, I always use but anyway, and so every beat that she uses, she just randomly picks either this basis of encodement or this one. And so she just takes her polarizing filter and shoots photon through the either this filter or this filter. And Bone doesn't know which filter she's using. And so every time he receives a photon, he also just randomly picks a filter. Is it this one or this one? And he just also writes down whatever he receives. So he receives, let's say, 1, 1, 1, 0, 1. And so obviously he received a completely different thing, and they cannot use a key yet. And so that's what they have classical channel for. But we'll get to that a little bit later. And then he sends he doesn't send this thing to her because then anyone can basically listen to their key. But what he does is he sends the whatever filter he used for each bit. So for example, for this one, he used orthogonal, then he used Hadamard, orthogonal, and Hadamard. And so he sends this to Alice, and Alice sends back her gates. And so what they see is they see which actual, sorry, not gates, the bases. They both see what bases they used, and they just cross out the ones that differ. Because, for example, if we used, let's say she was shooting something in orthogonal basis and she was shooting 1. So that was our vector. But then Bob used a filter that has polarizing axis here. And so because of that, we'll only have a probability of finding 1 on Bob's side to be 50%. And so because we don't know if you read the right 50%, we just cross out everything that didn't match in terms of gates. So for each gates that were not met, we just cross it out completely. And so we cross out, for example, she used Hadamard here, we cross out our orthogonal gate, and then she used maybe Hadamard gate here. We also cross it out, and then we cross it out here because she used orthogonal here. And so what we have is that we have the ones that she definitely received right. And even if we know that, for example, some bits match, we don't know that for sure because they cannot exchange their keys through the classical channel. And so they drop every value that did not match, and the rest is basically their key. And the advantage, okay, of this algorithm is basically if there is another person who, let's say, wants to like steal their key, they connect actually to the quantum part, not the classical one. Excuse me. First, they don't know which basis they're using. So they first have to find the right basis, but then even if they use the right basis, they will still interact with photons and they will change the polarization of photons. And then Bob will receive the photons that are polarized in a different direction. And what we see for larger set, okay, like here we use only 5 photons, but what they're shooting is actually way larger number. So on average, it will eliminate around 50% of qubits. And then statistically, if let's say Eve inserts their polarization filter, we will receive around 25% of qubits that of gates that correspond. And so that's really suspicious. And knowing that, the statistics, we can definitely say that somebody is spying on that. And so what this algorithm does is it not only provides a secure, fast way to encrypt our key, but it also tells us if somebody is spying on us. Not to even mention that the keys that you've received will completely differ from what we used here. So stuff like that. Any questions for getting that? And I think we're running short on time, so I would like Shireen to talk about her quantum project that she did.
Is the presentation there or?
Yeah, my presentation, I have it on my computer.
Okay.
Is everyone clear on how the key distribution works, or?
So that 50%, what's lost there? Just the photons, like 50%?
Oh, so around, what I mean by 50% is that on average, 50% of bases that he will choose will differ. Because when we talk not about like 5 bits, but we talk about 100 bits, you just randomly pick 1 and 1 and 1 and 1, you'll have like maybe like 49% matching or something like that, because when we talk about larger numbers, statistics comes into play, and because they're both just picking up different filter every time for each photon coming in there, around 50% only will match. And they're dropping the 50% that don't match, but it doesn't decrease the efficiency because then only they know what is left.
A little bit more on that. The 50% only corresponds to, I think, the classical choice of which basis you're measuring in. I think the essence of the key distribution is just matching that basis choice with the bits, and if both of those match, you have a good bit for the key. And otherwise, you can detect that Eve messes with the quantum bits if they differ, but you have the same basis. So. But anyways.
Yes.
Take it away.
Did we answer your question?
Yeah, I definitely need to read up on it, but I think I'm getting there.
I don't.
So hi all, my name is Shireen and I'm civil engineering. So if you know better than me, I know that in physics or mechanical engineering, please correct me because my background is the whole in civil engineering. So the motivation behind my project starts last semester when I took fluid mechanics, and we talk about motion in fluids. And I also joined a quantum club, and the idea came to my mind when we reached about Navier-Stokes, which later I will talk about it. In general, so basically, if you want to talk about motion it's based on Newton's law, you know, all of you, and in solid and fluids. But in fluids, it becomes to Euler's equation, which we talk about conservation of mass and momentum, and we consider it for a specific control volume. Sorry, the gradient symbol here is wrong because I couldn't find the right symbol. But yeah, the time and space in fluid is so important because it changes so quickly. And then if you in Euler's equation, it's for only in viscous fluids. For it only works for for example, if you heard of some potential flow or for ideal gases. But if you consider viscous forces in the fluid, it comes to Navier-Stokes because Euler's equation doesn't work for that. And so Navier-Stokes in the right hand, you can see the viscous forces and pressure and other forces that it force. If you imagine the very, very tiny particle in the fluid, these forces are like coming everywhere to the particle in the fluid. And in the left side, you can see the momentum in terms of time and space. So here, Reynolds number takes a huge role here because Reynolds number basically talk about a portion of the forces and viscous of the fluid. So why Reynolds number is important? Because in a high Reynolds number, you can ignore the viscous forces, but in very, very low Reynolds number, viscous forces can basically play a really, really important role. And if you, in very, very low Reynolds number, if you see the particle in the fluid, basically the particle couldn't move. And if it moves, it just stuck there. And why this is so important? If you think about a body in many parts of our blood vessels, we have a Reynolds number under 1. And so this is so important when it comes to drug industry, because when you want to reach out to the targeted organ, some of the medicines, they couldn't move to the Reynolds number under 1. So you need some forces to basically kind of, how can I say, take this drug to the targeted organ. Yeah. So what I did, I just talked with Professor Demir from mechanical engineering. She's working on drug delivery, and she suggests that because she said that she doesn't have any background in quantum computing, but she said that if I can start with simple simulation of the particle in the fluid domain, and then connect it with consider quantum computing there, because she was saying, so okay, I will.
Yeah, don't be too broad.
Okay. So for example, this is our domain to study or control volume. If you, so we can see, everyone can see. Okay. So if we consider in a very, very simple version of the problem, this is our particle and wants to move, and the Reynolds number is so low. So she was saying, when you want to simulate these, you need to solve Navier-Stokes. So Navier-Stokes it's based on works on partial differential equations. So when you want to run the analysis for partial differential equations, you need meshes, like kind of to apply the Navier-Stokes for the meshes around this particle or in your contour volume area. So in here, two things is so important. Yeah, one is geometry of the particle, and the second one is the meshes sizes. When it's so the sizes are so tiny, the analysis, the run, it takes so many. She was saying that it takes days for her to just run the analysis for the when you like change the sizes. Even in this particle, like it takes, for example, 20 minutes or 10 minutes. So so she was asking if it's possible to like start from this simplest problem and run the quantum computing for that, and maybe makes it in a shorter time, because even it's long time, but it also costs money, for example, in a very big project. So, and also the other thing I wanted to mention.
So why did you choose quantum computing for this problem? Like what aspect of it made quantum computing, I guess, preferable over the classical option?
I guess I'm not expert in quantum computing, but I think that quantum computing can maybe like kind of if I 1 second optimize the mesh sizes in classical, and it goes to quantum algorithms and apply quantum algorithms for these mesh sizes, maybe the error and the time will be so low, and our result will be so precise. I'm not sure about that, but yeah.
I would say in theory, definitely.
Yeah.
In practice, I think we forgot to mention today, for those who are new, that quantum computers are still super noisy. That's why they're not used in practice that much.
I mean, certain protocols, like communication protocols, yeah,
But it's definitely worth it to like start developing stuff like that now. So later, when we come to the era when quantum computers are already efficient enough, we can just like start applying the already developed algorithms like this.
I saw like so many papers to combine CFD, which is computational fluid dynamics, and quantum algorithms, and I'm reading that. It's so, I think for me it's so fascinating. I don't know how this one works, but I'm working on that, and it just one second. I will get back to you. Here she was saying that, so here the only this problem can be solved in two ways. One, if you consider particle is moving with a constant velocity in the fluid domain, or the particle is just stopped there, and fluid just moves around this particle. Which I am simulating the second problem. Fluid is moving, and so she was saying that here the only force around this particle is called drag force, and the drag force is 6 pi. I'm not sure about something, and I am changing the mesh sizes to get the specific precise result of drag force for this particle, and then we apply quantum algorithms if whether the result will be the same or not. Yeah.
You, when you said, sorry, when you said your problems might take like hours to days to calculate the result? Is it on your PC or some?
Oh, this is not mine for the professor, she was saying.
Yeah, what kind of computer it is?
Oh, the normal computers.
So,
Yeah.
have you ever considered like using a high performance computer?
I didn't ask her.
Yeah, I would say that might be a more feasible solution for your research.
I didn't ask her, but it was interesting for me that she was saying that, okay, I just leave it out there, run around one night, and I I will come back 2 days or the day
Yeah.
after that, and I will like,
So I mean, I had a project that like literally needs like hundreds of years for a personal computer. But what I did was like using a high performance computer and distribute the calculation to different nodes. It's kind of you are using tens of computer to do the job for you at the same time. Yeah, which will reduce the time significantly. Yeah.
I will suggest her.
Yeah, but I mean, of course, this will be more interesting than what I said, if you can do this with quantum computing. Yeah. That's a more feasible way as well, I mean.
Thank you. I will suggest. Yeah, any question?
Just adding on a bit to what Ming said, just like a quick aside, like there's actually a computing cluster on campus. It's called Soul, I think, if you wanna look into that. It takes a very long time to smooth under your computer.
Is it like what? What does this computing center does?
Yeah, it's just similar to what Ming said, it's like a computing cluster, so it has all these like computers that are specifically designed to take jobs and
Oh.
perform these calculations at higher speeds. They do it all in parallel, so you can like run multiple trials. Probably like over the course of a day.
I think it has 4,000 nodes last time I talked. That's a lot. They even have like a workshop where they teach you how to use it and they'll give you a certain amount of hours. So like for your project, I bet they would give you a couple hundred hours.
So can any professor apply?
It's through LTS. And if I remember correctly, they get some NSF funding. And they like want to spend that funding. So like they will, if you have a proposal, you go to a professor and then they will assign that professor like a certain amount of hours for you to use. So wanna use them.
Some good info.
And I would just add that like even if you try like either develop or apply certain quantum algorithms to that, and you show that it's ineffective, that's already a result, and there are a bunch of papers that just like benchmark quantum algorithms. They're like, okay, this stuff is not effective for this problem. And it's already like that's a whole research area to show like what quantum computing will be effective for and what not, so.
What kind of fluid do you use? Is it a elongational flow or is it a shear flow? How does it move?
How does it move? You mean like the fluid properties or?
Yeah,
So I just use the simplest version of the.
is it
fluid.
just moving in one direction?
Yeah,
Oh, I see.
moving one direction, and it's water, and the viscosity we consider one, and the velocity one, everything, the simplest version, just in case, yeah.
Well, I think. No. So thank you all for coming today. I think we'll close in this beautiful presentation. I love the background pictures. So yeah, feel free to stay after for a little bit if you have any questions or want to discuss anything. It was super nice to see you all today. And we're meeting next Thursday to cover chapter 3. And then we'll have, the week after that, we'll have some social event. So a little break from lecture. So thank you all for coming. Have a good night.
And we will probably post some things that if you'd be so gracious